The derivation sheet, proving the cross-product rules with the Levi-Civita symbol, provides a comprehensive bridge between abstract algebraic proofs and the physical mechanics of rotating bodies. It begins by using the Levi-Civita symbol as a logic gate to derive fundamental cross-product rules, demonstrating how index notation precisely governs the right-hand rule. This mathematical foundation is then applied to increasingly complex physical scenarios, such as 3D torque and the moments of inertia. To facilitate this learning process, the derivation sheet utilizes two primary conceptual frameworks: a state diagram and a sequence diagram. The state diagram, a progressive journey of complexity. The state diagram serves as a roadmap for the learner, tracing the evolution of complexity from basic algebra to advanced geometric mapping. Foundation and basic torque. The journey starts with the algebraic foundation, proving how the Levi-Civita symbol defines basis vector relationships. It then moves to torque 2D, applying this logic to a simple wrench-like scenario where force and position are confined to a single plane. 3D coupling and asymmetry. The complexity escalates in the torque 3D state, where tilting the lever arm demonstrates how a single force can trigger torque across multiple axes simultaneously. This leads to the study of asymmetric inertia, revealing how off-diagonal mass distribution causes rotating objects to wobble, because their momentum and rotation directions misalign. Alignment and synthesis. The final states, principal axis and the inertia ellipsoid, show how mass alignment simplifies these mechanics and how the entire tensor can be visualized as a 3D volume that maps rotational resistance in every possible direction. The sequence diagram. Logical and technical flow. While the state diagram focuses on the evolution of understanding, the sequence diagram illustrates the logical and technical flow required to move from theory to a simulated physical environment. Algebraic foundation. The sequence begins by initializing the mathematical engine, establishing that the Levi-Civita symbol is the fundamental computational driver for all rotations. Kinematic mapping. This layer applies the engine to torque. It transitions the logic from 2D planes to 3D tilted arms, using a Python-based visualization to show multi-index coupling in real time. Tensor analysis. The flow moves into tensor mechanics, employing the Kronecker delta to define the inertia tensor. This stage simulates the physical wobbling of unbalanced masses before solving for the perfect alignment found in principal axes. Geometric fulfillment. The sequence concludes by synthesizing the preceding math and mechanics into the inertia ellipsoid. By applying the parallel axis theorem, this final step demonstrates how shifting the origin of rotation fundamentally deforms the object's geometric map of resistance. By integrating these two diagrams, the derivation sheet ensures that the user understands not just the how of the mathematical derivation, but the why of its physical application in three-dimensional space.